probably not going to hold forever. And that's the topic of the article before. From the development 60s toward more available prediction of the exponential growth in the number of components on integrated circuits, which has been proven remarkably accurate by subsequent history immortalized in the field of Moore's law. Interesting logically upholding Moore's law by roughly doubling the number of resistors in this process every couple of years, but now that table is starting to slip. So I'm going to ask the somewhat provocative question is, should this concern us as computational physicists? And so this is maybe the answer, part of the answer. So you know that we can do parallelism, and this has a great deal to overcome these limitations. So going into my talk, I will talk about how we use parallelism in molecular dynamics. And I will also talk about Monte Carlo methods. And the third one I will give an overview of benchmarks we've done to measure the performance of our codes, and finally I'll go to some applications. So first, so in software and matter physics, we have two main kind of methods which we're using for simulations, and these are molecular dynamics and Monte Carlo methods. And this is just an overview of some of the things that we do in our research group, including quartz crystals, tablets, nanoparticles, photons, nanoparticles, self-orbital particles, and the molecular dynamics side. And we can do molecular dynamics whenever there's a short-range potential or a potential that's sufficiently smooth so that we can take the difference built out of it. And on the other side, there's Monte Carlo, which we use for shapes, such as truncated tetrahedron or convex polyhedron, polygons, and disks. This is the method of choice when we don't have a differentiable potential, so we need to take into account the sharply positive nature of the interaction between the particles. And we do all of our studies, and most of our studies do with our code that we write in this HOOMD-blue, and it has been used in a variety of different studies in literature, over 100 publications this year. So molecular dynamics is a method that iteratively solves Newton's equation of motion. And does this, but usually in a kind of very easy, second-order accurate. And this iterating through this set of equations of motion is not very hard. Actually, it only has one difficult step, this computation of forces, which is not really linear in complexity, but O(n squared. But if you do it with the right kind of data structures and algorithms, you can break down this computation to linear computation, and then you have a nicely parallel algorithm that beautifully scales. So this is how you do molecular dynamics on a single GPU in parallel. First, you have the particle simulation domain, and the first step is to break the simulation domain into cells that hold subset of particles, and then you have to assign particles to the cells. And on the GPU, you do this by assigning one thread to one particle, and then using atomic operations to sort the particles into cells and implement the cell counters. Next step is to build a neighbor list. The neighbor list we construct from the cell list, and includes all particles that are within the count rate as a single particle. And again, we do this by assigning one thread of the GPU to one particle. And as you may guess, this is the same proportion for the gaffers. Now the gaffers per particle are thread, and every thread looks over the names of the particle that's been defined in the name list. And finally, when all these forces are included, we sum them up and integrate the equations of motion, and finally, again, this is one thread product. So the take home message is molecular dynamics in the GPU is a pretty straightforward thing to do. It requires you to map one thread and one particle. And also parallelization across GPUs is also not in principle good. What requires is the same idea as for the decomposition of a single simulation domain. We now now split the whole simulation domain into subdomains that can communicate between particles that are migrating from here to here they have to be sent across some network. And for working computing the forces between the particles, we have to additionally take into account the particles that lie in the boundary of the domain. They have to take into account particles that are on the other side of the boundary, so we have to communicate those particles back and forth. And all this requires communication every time step. But otherwise, it's not something that's very difficult to estimate. And also, it's easy to use with HOOMD. So, HOOMD is a program script by Python scripts. This Python script here is everything that's needed to simulate the system, in this case, of some initial configuration in constant temperature over 100,000 time steps. You start by doing configuration, defining the gap potential, and setting the time step, and then integrating at some temperature over a number of steps. And if you know how to use Python, then you probably also know how to use HOOMD. And if you don't know how to use Python, you can still use HOOMD. The next application we are developing is a plugin to HOOMD that enables us to do Monte Carlo on the GPU. And as I said, like Monte Carlo is an algorithm that treats sharply positive potentials. It's also an algorithm that's inherently sequential. So I did one particle at a time, then the next particle, and so on. However, there are ways to parallelize the Monte Carlo on GPUs and across GPUs. This is one method that is being developed in our group. It's not yet part of HOOMD officially, but it will be eventually released with HOOMD. So what does it do? It can simulate, for example, these complex states of Wilkes, which form these unit cells, which have a structure of 20 particles in the unit cell, or in very, very complicated arrangements, complex arrangements. It can do these quantitative form diamond with 8 particles in the unit cell. It can do arbitrary complex polymer and starts of set phase disks. And it can do other shapes as well, such as colloids, 3D, zero polyhedron, concave polyhedron. There's quite some options for the user. And it's capable of doing that different ensembles, it has different integrators. In the CPU, it uses an optimization for fast polymer, and it's capable of doing simulations across GPUs or CPUs in the automated composition. You may be wondering how this is working with Monte Carlo, as it's a zero algorithm. By zero algorithm, I mean really that if we move one particle, we displace by the amount, then we accept or reject the move, and our particle acceptance or rejection is very simple criterion. Whenever it overlaps with a different particle, the move is rejected. When it does not overlap, the move is accepted. That's really what we have to guarantee. To parallelize this scheme, we observe that when we grid the space into a grid where the cells are of exactly the particle size, or something above, then we can, as long as we do not move particles outside the boundaries, we can move every second cell of the grid in every dimension in parallel. So that means we can count the grid as a checkerboard. And we can update those cells independently, which are separated from each other cell by one layer of inactive cells. And to switch the colors, that means that we switch the active cells to make them inactive, vice versa. And once we iterate about the colors of the checkerboard, there are 4 of them in this case, we have done one sweep of Monte Carlo. And to guarantee that this is actually a periodic simulation, that means that the particles do not always stay inside the cells. The only step which we have to ensure is that we have to move the grid, shift it randomly in some direction, and that's basically what's needed to do Monte Carlo parallel. And as you may imagine, this doesn't only apply to the GPU, where we map the cells of the CPU Discoids. This also works for whole simulation domains, which are separated by the domains by an inactive layer. Okay, so this is the Monte Carlo method, and this is how we use it. Again, it's applied to HOOMD, so all you have to do actually is to first apply the unit configuration, and then you define the shape. In this case, it's a polygon. The polygon is defined in this case by 4 vertices, so it's square, and you run it for some time, so it gets a Python scripted program. And the last method I want to introduce is a refinement of the Monte Carlo method. It's a method that is applicable when you have large particles divided into small particles, which is something which is actually very computer intensive because of the size disparity between these two species of particles. And when there are many small particles around, that means you spend a lot of time integrating all the small particles. And what this picture tells us is that the large particles in the path of small particles actually like to come together because they maximize the free volume available to the small particles by polyping into the volume shells. And that leads to an emergent attractive interaction between the large particles. I developed a scheme that allows us to simulate these systems with an implicit backup of small particles. And the nice thing about the scheme, I don't want to tell you in detail why this is an exact scheme, is only that it's a parallel scheme. So I can randomly place small particles on the large particles, in this case on the squares. When I move large particle, I can place these small particles independently. And what I get from this is that I can integrate out the effective interaction between the large particles by randomly placing small particles in parallel, without actually having to simulate small particles in memory. And this gives me a huge speed up, for example, when I have systems where I have a few large particles and a lot of space around them to otherwise be filled by small particles. And this is just to say it's really working as it's supposed to do. I have explained to you the methods, and just to recap the methods part, we learned that, or we did that molecular dynamics is basically the perfect parallel algorithm. Particle Monte Carlo is a theory algorithm, but it can be parallelized using Chekhov schemes. In simulations where we have large particles and small particles, we can take advantage of further parallelization using implicit depletion methods. Okay, now on to the performance of these codes. In CPU, traditional CPU molecular dynamics codes, the balance between the network and the processor is actually quite advantageous because the CPU is a zero-bit processor and takes the time to process the workload and before it requires any interaction with another CPU. That means that the infinite band network or whatever PCIe-based networks between the CPUs is most of the time sufficient to ensure scaling of CPU codes. With GPUs, the situation is drastically different because GPUs just so massively parallel processors with thousands of cores and extremely fast processing speed. The PCIe bus network becomes a thin straw, and we'll actually find ourselves limited by the time spent in communication. In development of HOOMD-blue, we address these limitations and aggressively optimize HOOMD-blue for strong scaling situations and also weak scaling. And that this works, I will show you the following. This is a benchmark of HOOMD-blue rescaling on a type machine with a benchmark that has 32,000 particles on a single node and it scales out the number of nodes to 3,750 nodes. And we see that the performance is overall dropping by a factor of 4 when going from 1 to these almost 4,000 nodes. But most of the half the drop occurs actually when we go from 1 to 8 GPUs, which is just an artifact of increasing the dimensionality of the domain decomposition from 1D to 3D. And then it's a factor of 2 over 3,000 nodes, so that's not nothing too bad for rescale. And it's twice as fast as AMP in this case, and has good performance numbers, so that also is reassuring. In strong scaling, the situation is equally good, I would say, after we applied these optimizations. And we get the speed up that's linear for up to 32 GPUs, and then continues to scale to 1024 GPUs. Again, in strong scaling for an advanced particle development of 10 million particles, HOOMD-blue is a factor of 2, roughly constantly faster than MEMS. And what's interesting here about this comparison is that MEMS was optimized for the Wilkes machine when it came out in a way that can take advantage of the CPU cores that are otherwise idle in the nodes. But this doesn't result in any speed up relative to our applications we see. HOOMD only uses one GPU per node, and one core corresponding to drive that GPU. In more realistic applications, when we not do just Jones particles, but polymer brush, for example, which are tapped into a substrate here, then we can scale the XY dimension of the polymer brush and produce systems of different sizes, and we can scale the number of GPUs to run the system on. And we see that the scaling of the linear scaling holds up very well, also when we do these more realistic systems, we include end bonds, tetrahedral bonds, covalent bonds. And we get a speed up over a node of CPU cores, which is 12.5x, so that's also something that's significant and expected for GPUs always. And in dissipative particle benchmarks, we get a similar situation where we scale strongly out to 40 nodes. And we see our memory that in this down precision benchmark, the performance between the different codes we have measured to other codes is roughly similar qualitatively, even though that HOOMD-blue scales better for smaller GPUs, but then codes approach each other. So that basically indicates that we are capable of hitting the limits of the hardware in a way that's independent of the kind of implementation on the software side. And that we are pushing these limits to. And this is the slide that most pertains to this user group meeting. So we measured the performance of HOOMD-blue when it's enabled with GPUDirect RDMA, and found that, so everyone in this room has had some exposure to GPUDirect and we on this for the days, offload the CPU from the communication part. We find that single precision GPUDirect RDMA doesn't give us the use advantage over heavily optimized and dark holes with host buffer memory staging. However, in that decision, there's some slight advantage in strong scaling situations as for GPUDirect RDMA versus host memory. And as you point out this morning, I've seen the benchmarks for advantage 2.1 RC2 with 26% increase of performance over these last numbers. So if you take those into account, I would guess that GPUDirect RDMA is faster than manually optimized in Young. And I need to confirm that. I wasn't able to this morning because we had some issues with the installation of the entire library and the server to solve these out for the group.
Yeah, this is going to solve. There is something we learned in Century.
Oh, that's very bad turnaround. So and finally, the scaling for the hardest Monte Carlo is a little qualitatively different. You can do this on GPUs, up to 64 GPUs. You can do this on up to 4096 CPU cores. And what's noticeable here is that the GPUs are, of course, higher performance, roughly a factor of more or a magnitude versus the zero CPU core, 29 is the factor. However, the GPUs cease to stay when the number of GPUs involved becomes high, whereas the CPU scale to a high absolute performance in this case. This is not too surprising for us because we know that the current list inherent to the Monte Carlo algorithm is limited compared to the one in the text algorithm. To summarize this part, when it comes to GPUs, we know that communication is basically the most limiting factor. And it allows us still to extend the source scale up to thousands of GPUs. And this is different with hardware to Monte Carlo, where communication is not really the limiting factor, but the CPU cores demonstrate that scalability of GPUs there. And finally, I want to talk about some applications we have been doing with our codes. And the first one of this is block polymer simulation. So we're interested in how these dipole polymers, which are polymer chains of two chemically distinct species of A and B monomers that are tethered together, microphase separate and form these lamellar structures when cooled down under the phase transition temperature. And so this study was all about finding the phase transition temperature for different kinds of chain models and different chain length. As much chaining we find in the universal dependence of the transition part that was on the invariant chain length. And to take this study, it actually required us to do massively powerful simulations on hundreds of GPUs over the time of several days per state point. And this study used something in the order of 500,000 service units on the XC network within 2 months and almost brought us to the end of our location very quickly. And it wouldn't have been possible with multiple GPUs, more. The next example I'm showing is about the large and small particles. So if we put these Discoid colloids in a solution of in the bath of explicit depletants here, then we see that most of the box actually filled with small particles. And it means that we cannot simulate the whole system in reasonable time. We have to integrate our 200,000 small particles just to move these 500 plus particles around. And with implicit simulation of the small particles, we actually able to see clustering of the large particles, which nicely confirms that the implicit method is working as it should, and it has tremendous performance benefit. Actually, it enables us to do the simulation. And this is an example from the actual simulation showing how the Discoids aggregate into short straddle configurations. So they start with this orbit and then they form these metastable straddle configurations. And this simulation has been run in parallel using company around 64 cores, using MVAPICH2 on the common cluster. And here we have an example how the GPU execution is favorable and has performance at small colloid penetrations like this. This is about 0.02, I believe. So this is here where the GPUs really have an advantage. GPUs don't have so much to polymer system is dense, which is related to current parallelism current system. And this is the last example I'm showing you. It shows a system of very simple particles, the hemispheres, which are spheres held on the equator, and put in the box at 57% packing fraction. And what we see is that what these hemispheres do when there are small particles which are not visualized in the system around them, they like to come together and this is what you expect. And if you look at this simulation, you can see what's happening. So we see that the hemispheres, spheres, and the spheres themselves are formed fluid, but then the fluid itself after some time organizes, as you can see in the correlation of the bonds in that system, and the fluid crystallizes into HCP lattice. So now we have a fluid of clusters of hemispheres, which form crystal. And this was done again using a parallel execution of HPMC on 8 CPU cores. This shows that there's a space diagram where these structures occurs, and we can compare the performance of hemisphere aggregation across different nodes. So we can do it with explicit small particles, then they never form the order phase. We can do it with a canonical path of explicit particles that actually do form the phase, but later than when we do it with the accelerated code. And this brings me to the outlook of my part when I talk. So this is what we're interested in. We want to scale up our simulations to really large numbers of cores or GPUs. And what I'm showing here is the performance of 3 different codes, molecular kinetics, Monte Carlo, and DNM. I haven't talked about DNM already. as a function of the number of GPUs used to do that computable benchmark. And here it's across almost the whole range of GPUs available in the Python machine. And we see pretty decent scaling exponentially for molecular dynamics. 16,384 GPUs in parallel. Of course, this is not yet what we do today. So we're able to run benchmarks on these systems, and we can measure performance and get meaningful numbers. However, what lacking for us is basically the input on the availability of scientific questions that we can realistically ask and that warrant simulation on such large scales. So we have the codes, but the next step would be to do the routine samples on such large machines. And I think this is at least as big a challenge for scientists to find out how these tremendously powerful tools are being utilized as just building them and writing software for it. To summarize, we have seen, okay, we'll start this slowing down, but hey, we cannot afford to wait 2 years for the next W performance anyway, so we need parallelism today. And we expect parallelism by using GPUs, threads, vector instructions, and API. And this enables us to build high-performing simulation codes. And with parallel codes, essentially what we are able to do is to solve those problems which we have been able to solve previously. So with this, I would like to thank you for your attention. And on Monte Carlo and download on the website, there's a paper on the source paper from Digo, and the Monte Carlo will eventually release along with HOOMD-blue. And looking forward to any questions you may have.
Okay, so let's stand to any questions? You had a 384 GPU on which machine did you run that?
That was on the now decommissioned Univ cluster.
Okay, okay.
Yeah.
Any other questions? There are a lot of nice pictures. So the molecular dynamics work is taking place. So thanks then again, gents. So let's move to the next talk. Will be given by James Lewis from CSTAP. James is a CUDA research. Does the CUDA research with CSTAP. He studied at the University of Utah Scientific Computing Institute, where he received Bachelor of Science degrees in both computer science and applied mathematics, as well as